So now I want to define B trees formally. What is a B tree? So a B tree is a rooted tree. It is a rooted tree with the following properties. The first one has to do with the node and what's in the node. What do we store in that node? So the first one is that for every node X has the following attributes. And I will visualize it like this. So imagine that this is node X. And node X is going to have a field that's called x.n. So for every node, it will have a field n, okay, or an attribute n. What is x sub x.n? This is the number of keys in node X. Okay? And in addition to that, we are going to have x.leaf. X.leaf is a Boolean flag, and x.leaf is this one here. It is true if X is a leaf and false otherwise. Okay, so this is just a flag that you check. If it is true, then this node is a leaf. It has no children. Otherwise, it is false. It is not a leaf. In addition to this, we are going to have the n keys themselves. Okay, so the keys are, imagine that there are some elements of a set that is totally ordered. So I can say key 1 is smaller than key 2, key 2 smaller than key 3, and so on. So now we are going to have n keys. Okay, so I'm going to have x.key1, and we will have x.key2, all the way we are going to have x.key x sub n. Okay, the index of the last key is x sub n because there is x sub n keys, right? So the first one is key 1, key 2, all the way to key sub x dot n. So these keys again are numbers or some names or something like that we can actually impose on them some order, and that order is the order is x dot key 1 is smaller than or equal to x dot key 2 smaller than or equal to x dot key sub x dot n. Okay, so the smaller than or equal, again, it is a less than or equal for numbers and so on, but think about it as it is a total order on the elements. Now if you look at these n keys, they are going to define for us, they will define for us n pointers that point to children of this node. So here we will have pointer x.c1 for child 1, x.c2, and so on, all the way to x.c, again, sub x.n. So each one of these is going to point to a subtree, okay? So this will point to a subtree, and so on. Let's label this T1, this is T2, all the way to T sub x sub n plus 1, right? So if you have n keys, we have n plus 1. Sorry, here this should be, in this one here at the end should be xn plus 1. There are x sub x dot n plus 1 pointers to children or to subtrees. Now we are going to have an important property of the keys in these subtrees. Okay, so if I label, for example, if I label ki is a key in subtree ti, okay, so ki, let me actually erase and write it cleaner a little bit. So if I write ki is a key, any key in subtree Ti. Okay, so in T1, any key there, I will represent them by K1. In T2, I will talk about K2, which is a key in tree T2, and I will talk about K sub x dot n plus 1 as a key in the tree T sub xn plus 1. Then if we have these keys, we are going to have the property that K1 has to be smaller than or equal. So any key in T1 has to be smaller than or equal to x dot key1. And that x dot key1 has to be smaller than or equal to every key in tree T2, which must be smaller than or equal to x dot key2, and so on. And then at the end we get to, for example, that we will get to kn smaller than or equal to x dot key dot xn. This is not kn again, sorry. It is x dot n, and this is smaller than k dot xn plus 1. Okay, so we need to have this property satisfied for all the subtrees that these x dot n plus 1 pointers are pointed to. Okay, now this is very important about the node, because this is this important property is what will allow us to know when we are looking for an element to what child of the node we go to. As I'm descending down, for example, to the leaf in the worst case while looking for a key, then which one I need to go to. Okay, so a node has to have x dot n, which basically tells us how many keys are in the node, x dot leaf, which is a Boolean flag for saying whether the node is a leaf or not, and then we have to have x dot n keys. These are x dot key with the subscript, and then we will have x dot n plus 1 pointers to child nodes of the tree, and we have to have that important property about the keys in the node as well as the keys in the children of the node. Okay, in addition to this, in addition to all these properties, of course we want the tree to be balanced, and this is a very important property here, is that all leaves or all leaf nodes have the same depth, which again, every leaf, it means, what this means, that all the leaves have the same length of a path from the root to that leaf. Okay, and this depth is also the height of the tree, which is the height h of the tree. Okay, so the tree, all the leaves have to be at the same level, which is not a property that we demand or require of binary search trees of red-black trees. Okay, in this case, the tree all the leaves have to be at the same level in terms of depth from the root. And the last property here is about the branching factor of the tree. So we said binary search trees and red-black trees, every node has at most 2 children. But here, what about the children? Is it unbounded? The answer is no. We associate with every tree, we associate a factor or a parameter that tells us what's the minimum number of children of a node and what's the maximum number of children of a node. Okay, so we associate with the tree, is a parameter, t, that is greater than or equal to 2, such that this is the t that will control the number of children of a node, such that for every node x, other than the root, okay, this is very important here. I'm not talking about the root. Every node x other than the root has to satisfy that the number of keys in that node has to be at least t minus 1 and at most 2t minus 1. Okay, and let me just talk about the root here, and then we'll talk about a specific example for t. For the root, r we have that r dot n is at least 1, but in terms of the upper bound, it is still 2t minus 1, okay? So what we are saying here is that regardless of what t is, the root has to have at least one key, okay? For every other node, including the root, the node has to have at most 2t minus 1 keys in it, okay? So if we take for example, t to be 5, let's talk about t equal 5. So what is this saying about every internal node other than the root? That x sub n is somewhere between 4 and 9, okay? Now, if we talk about a full node, which means it has the maximum number of possible children. It will have 9 children, okay? And if you think about the other extreme, a node that has the fewest children possible, if we talk about node with the fewest children, it has 4. Now look at 4 compared to 9. What we are saying that with this t, what we are saying with this condition here, roughly speaking, that a node has to be at least half full. Any node has to be at least half full, okay? Full. And I'm not talking about, of course, a leaf node, because a leaf node has no children in it. But if you have a node that's not a leaf, and the maximum number of children it can have is, the maximum number of keys it can have is 9, then the minimum it can have is 4, which is, again, roughly speaking, is half the number of keys. And this is very, very important here, because we can define other versions of these trees. We can say, for example, that the node has to be at least 3/4 full, okay, or 7/9 full, and so on. These will be different types of trees. For a B tree, we are using this t so that we guarantee with this property that the number of keys between t minus 1 and 2t minus 1, we are guaranteeing that the node is somewhere between full and half full, but it cannot be too sparse in terms of number of children. So if you take t to be 10, for example, then the number of keys has to be somewhere between 9 and 19. It cannot be 2 in that tree, okay? So these are the properties or the formal definition of a B tree. Again, the first one talks about the node will have some n keys and n plus 1 children. The keys in the children and in the node itself must be sorted in non-decreasing order. And the second important property is that the path from the node to a leaf is the same for the length of the path from the root to a leaf is the same for all leaves, or in other words, all the leaves are on the same level or in the same depth, which is the height of the tree. And the last one here is that this branching factor of the tree, which talks about the number of children, is that every node has between t minus 1 keys and 2t minus 1 keys. Remember, this is the number of keys. If a node has t minus 1 keys, it means it has t children. If it has 2t minus 1 keys, it means it has 2t children, okay? Because the number of children is the number of keys plus 1, okay? Again, please keep in mind that for the root, you cannot have no keys, okay? The root has to have at least 1 key in it, okay? So this is the formal definition of a B tree. And based on this definition, actually, we can easily establish that the height of the tree has to do with the log of the number of keys in the tree. But the log now is not to the base 2. It has to do with this t, because that's the number of children that the node can have.